So let's just get the right ideas back in mind. So we were talking about the SYK model. There's the Lagrangian defining the model. And one of the things that we said was interesting about this model is that it's solvable. And what we meant by that was we were actually able to calculate correlation functions at large n. And we were busy setting up perturbation theory. We're going to continue with that. And today we're going to calculate the two-point correlation function. So the Lagrangian can be broken into two pieces. There's the first term I call our naught. It's used to define the free theory and the propagator. And here's the interaction term. If you do the path integral over just a pair of fields with e to the minus s naught, that's the answer, delta ij g naught of t. So g naught is 1/2 times the sine of t. And for this specific Green's function, we calculated that yesterday in the tutorial, so we saw how that works. As usual, so s naught would just be given as an integral dt over L naught. If you're working at zero temperature, you will integrate from minus infinity to plus infinity. If you're working at finite temperature, you would integrate from naught to beta. Okay, so now let's get on to our two-point computation. So what do we actually want to calculate? And I want to discuss some of the contributions and then show you how do we manage to sum everything. The reason why we are going to discuss some of the contributions now is so that you can see that large n actually simplifies the calculation. And we want to see how large n simplifies the calculation. So what we want to compute, we want to compute the following. We want to calculate now the time-ordered correlation function, phi a of t1, phi b perhaps of t2. And this is now the full interacting theory. So I can again express this as a path integral. And the path integral will be the following. So I'll have the integral d chi I will have e to the minus s chi a of t1 chi b of t2. Now this is rather different to what we were considering there. And the reason why it's different is the action here consists only of the free term. Over here the action consists of everything, the free term plus the interaction. Now the only kind of integral that we can really calculate, that we really know how to do, is a Gaussian integral. So how are we going to deal with this case where it's not a Gaussian integral, because we have both a term quadratic in the chi's, that's good, that'll be a Gaussian, but we also have a term quartic in the chi's. So what should we do in this case? Set up a perturbation theory. And what we would do is, we would expand in the interaction Lagrangian. So we will write this as an integral d chi I e to the minus integral L naught dt. That we don't expand. But then we would have a second term here, e to the minus integral L interaction dt. And we're going to expand the e to the minus integral L interaction dt. If we expand an exponential, we'll get 1 minus an integral, the interaction Lagrangian dt, plus 1 over 2 factorial, the interaction Lagrangian dt squared, and so that will continue. So this sum together will produce the second exponential, and then we would have chi a of t1, chi b of t2. Are we all following? Okay. All right. Now, I'm going to name these terms something, okay? So let's call this first term A. Let's call that second term B. Let's call that third term C. Now, whenever you're doing something non-trivial in life that takes a lot of work, and if there's a group of you, you should always do it together. So we have 3 terms there. There's a lot more of you than there is of me. So I think what would be a good idea is, I will calculate a term, and you guys should also calculate some terms. Okay? So I'll start off, because I know no one likes to go first. I'll calculate term A. So d chi A, e to the minus integral L naught dt, chi A t1, chi B of t2, and I take a look, this is e to the minus s dot, so lucky for me, it looks easy. So delta AB g naught of t1 minus t2. Great. I've done my bit. Now it's time for you guys. This was A. Let's write down the integral that needs to be done for B, and then maybe you guys can tell me what it is. Integral over the chi's. You have e to the minus integral L naught dt. Now we need 1 power of interaction Lagrangian. There is a minus there, the interaction Lagrangian will change signs, so it'll be a plus. We have a j, I, j, k, L over 4 factorial. Then we have an integral of t by j, t, j, k, L, M, chi k, chi L, chi M, t. And this is still times by chi A T1 chi E of T2.
Just a question. When we do the average, do we take the average of J as well?
Absolutely. So in fact, this is the first contribution to the correlator where the random coupling is appearing. So to get the answer here, we need to do 2 things. There's one average that we're calculating over the chi i's. Okay? And when we want to denote that average, we always use something like an angled bracket. Okay? So if I want to calculate an average where I've integrated in the path integral, I will always denote that average in that way. The disorder average, which is also a kind of an average, I will always denote with a bar above it. This one, I think in my mind, I've done 10,000 experiments with 10,000 different systems, and I've averaged the correlation function. This kind of an average is slightly different. I've integrated over all of the fields, and there's a quantum averaging that's going on. Okay? But indeed, I have to do both. Okay, good question, Andrew. Does that tell you what the answer is?
0.
0. Why?
The average of J0.
Very good. Okay, absolutely. So this is equal to 0. I want 2 reasons. We've already got 1. So the first reason is the average of J, K, L, M is equal to 0. Superb. Yes, Jeff?
You've got 6 car fields there, so when you recontract, you're going to get a delta KL maybe or something.
Very good. So can you see that when I start to Wick contract the chi fields, I can contract these 2 chi's with each other. Then I have to contract 2 chi's here. That's going to say 2 indices equal to each other. That's going to vanish. Or I could try to contract 1 chi here, another chi here. I'm still left with 2 chi's. When I Wick contract those, it will still vanish. Okay? So in fact, we vanish because of the disorder average, and we vanish because the Wick contractions over the chi's sets 2 indices on J equal. So, Wick contraction on the chi's sets 2 indices equal. Good. So that's two reasons why it's naught. So that's great. We've calculated term A, and we have calculated term B. Now let's look at term C. Now, term C should look somewhat familiar because this is one of the things that we discussed in the tutorial. Okay? And I'm going to write it like this. Just shout if you don't like my notation. Okay? Let me know and we can talk about it. So, 1/2 integral dt integral dt prime. These two integrals are coming because I now have two powers of the interaction Lagrangian. Each of those is an integral over time. That's where those are coming from. Then we have our fields, chi A of T1, chi B of T2. And then we have our two powers of the interaction Lagrangian. So let's say multiply by J, K, L, M, chi J, T, chi K, T, chi L, T, chi M, T, times by J, N, P, Q, R, chi N of T prime, chi P, T prime, chi Q of T prime, chi R of T prime. And I'm going to put a note to indicate I'm taking this average in the free field theory. So I'm integrating the chi k e to the minus s naught of all of that stuff there. Happy with the notation? Okay, now what kinds of things could we do? What kinds of contractions could we consider? So what do we need to do? We're doing this for the free theory. With the free theory, we've got integral e to the minus s naught. That is a Gaussian integral. Whenever we have a Gaussian integral, we said we could use Wick's theorem. How do we use Wick's theorem? We group things into pairs, and for each pair of chi's, we replace the pair by delta ij g naught of t. Okay? So we want to group this into pairs. So can you tell me what kinds of ways have we got of grouping things into pairs?
Taking A, B,
Good. So I'm going to put below here A, B, J, K, L, M, N, P, Q, R. And each of these corresponds to one of those fields. And now I'm going to say how I've paired them. So I could, if I like, have paired A and B. So that's one pairing I could do. What will I get if I decide to pair J and K?
0.
0. Because I'm going to be setting two indices on the J equal to each other. In fact, I cannot pair any of the first of those four indices without getting 0. And I cannot pair any of those indices without getting 0. So all that I can do is pair the indices in the first four with the indices in the second four. Okay? So what kinds of things could I have? I could have that, 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 that. Okay? So that's the kind of thing that we would have. What does this look like? So if I have to write down the contribution from this diagram, what it will look like is something like this. An integral dt, an integral dt primed. I will have, I've paired A and B, so I'll have a delta AB, and then I have paired J with N, K with P, L with Q, M with R, so I will get J, J, K, L, M, J, J, K, L, M. You see, consider the pairing of J with N. This is going to give me a delta Jn. So it's going to turn that N into a J. Okay, which is why I've then got that sitting there. And then I will have a G naught of T1 minus T2. And I will have a G naught of t minus t prime raised to the power of 4, because each of these contractions give me the same Green's function. And then the burden of the work, and this is what you guys would have to figure out, is what is the coefficient that sits there? So you need to work that out. If we draw this in a Feynman diagram, this diagram would look as follows. Our interaction has the J, it has a chi J, chi K, chi L, J M. So this is 4 fermion lines for the vertex. So there's 4 fermion lines. So this could be J, K, L, M. The second vertex also had 4 fermion lines. And we've actually paired these lines. So when we draw solid lines, what does the solid line keep track of? It keeps track of the way we have paired the chi's. That's what you're drawing in the Feynman diagram. Okay. And then we also have a pairing between A and B. And you could put a T and a T primed, a T1 and a T2. And then each line is translated into G naught of T1 minus T2, or G naught of T minus T prime. And all of the ways of drawing the lines are just your way of enumerating the different pairings. So that's what the Feynman diagram does for you. Okay? But we need to indicate something extra. This is what you would have in the usual field theory. What we need to indicate in addition is that we're not only averaging over the chi's. We are also averaging over the j's. So the notation that is usually done to do this, we have to combine the j's into pairs. So we would need to average the j sitting at this vertex, if we now draw by a dashed line, with the j sitting at that vertex. So we include an extra dashed line going between vertices to say how the different j's have been paired. Okay? And we would need to do that. Now, this is an example of a disconnected diagram. There's our propagator. That diagram sitting over there is disconnected. How can we get rid of the disconnected diagrams? So they will exponentiate, but do you know how can we get rid of the disconnected diagrams? Okay, so you should do some reading on this. If you normalize things so that the expectation value of 1 is equal to 1, so that's just a normalization choice. So normalize things so that the expectation value of 1 is equal to 1 in the interacting theory, then what will happen is that normalization will exactly subtract off all of your disconnected diagrams. So we don't need to worry about this at all. Okay? So this is a very usual thing in quantum field theory. You might have heard it also under the name of subtracting off the vacuum energy. And that's the same thing. Okay, so subtracting off the vacuum energy will get rid of all of those disconnected diagrams. We are always going to assume that we have normalized the expectation value of 1 equal to 1. And from now on, the way that we're going to implement that is we're just not going to draw Feynman diagrams that have a vacuum diagram piece. So a piece of the diagram that's not connected to any external points. Okay? So we won't include this diagram. Then this was just some practice to see how it worked. Good. Now, what's another way that we could start doing the pairings?
You can pair A with one of the first 4 and B with one of the second 4.
Good, okay. So that's your suggestion, David? Yeah. What about if I decided to pair B with K?
You get 0.
Does everybody see that? Comparing B with K means that even if we take these two into the last 4, we have to pair 2 of the indices in the last 4. Okay? So this is the only kind of a contraction we could do that would lead us to something that is non-zero. Okay? And so that's what it would look like. And then the remaining pairings would start to equate indices together. Okay. Now, so we're going to write down this diagram, but I would really like to know how big is this diagram. And to do that, we need to remember something. We need to remember the following. So if we had J, I, J, K, L, J, I, J, K, L, and we calculated that average, does everybody know how big this was? As a function of n. So there was a J squared, which was setting strength. There was a 3 factorial, let's not worry about that. Okay? But how did it depend on n? Over n cubed. Absolutely. So this was over n cubed. Good. And now we're going to keep track of this n dependence, because you see, the first thing that we've calculated is independent of n. So what we would like, if we've got a nice expansion, we want the term that we're going to add to also be independent of n. We don't want it to blow up as we take n to infinity. We don't want it to vanish as we take n to infinity. We want it to be the same size as that. So are we going to see that? Okay. So let's now calculate this particular value. So there's our A. There's our B. Now, first of all, and you can see I've collected 3 indices to 3 indices. So that's why I've got 3 on this vertex connected to 3 on that vertex. If this is I, we know that'll be set I. If this is J, that'll be J. If this is K, that will be K. These are all signed. If this is A, this had better be A. And if that's A, this will be A, because these 4 indices must match those 4 indices for the disorder average to be non-zero. So when we take a look at this, we're going to get a delta AB from there. We get a delta AB. What are we going to get from the top line? Delta I. Delta JJ. Delta K. And then we can put on the Green's functions. So this is T1, this is T2, this is T, this is T prime. G naught of T1 minus T, G naught of T prime minus T2, G naught of T minus T prime cubed. And you'll again have to figure out the coefficient. We do know we get a J squared over an N cubed. Now, I, J, and K are summed. So what is delta II? N. N times N times N. This here is N cubed, which cancels with the N cubed. So how big is this diagram? Order 1. When we take N to infinity, this is the same size as the leading term. It does, however, have this J squared sitting here. Okay. So what was important was the size of the diagram, and you guys will have fun getting the coefficient exactly correct in the tutorial. Okay. And of course here, I haven't finished drawing my Feynman diagram. I should do that to indicate how the disorder average was taken. Now, if we had kept expanding, the next term in this expansion would have been the cube of the interaction Lagrangian. What would that term have contributed? 0. Why 0?
Because if we contract 2j together, there would be
1j left over. Perfect. Disorder average would force that term to vanish. So the next non-vanishing term is the term with the interaction Lagrangian raised to the power of 4. In which case, how many vertices would we have? 4 vertices. Okay? And now we get some interesting possibilities. So, we get the following. Okay? One, two, three, 4 interaction vertices. But now we have this interesting case. When we do the disorder average, we could decide to pair the J's like this, or we could decide to pair the J's like that. So I am curious to know what is the end dependence in these two cases. Okay? You have 2 minutes to try to write on your page what you think the end dependence for these two diagrams will be, and then we'll do it together on the blackboard. Okay guys, let's take a look together. So let's take a look at this first one. If that's A, this side must be A, because the Majorana propagator sets the two indices equal. If this is I, J, K, then in this case, the disorder average is between those two vertices. So these three legs get set I, J, K, and that's an A. In this case, these three legs get set I, J, K, and there's A and A. Okay? So the disorder average sets the indices of this vertex equal to the indices of that vertex. Okay? This is A, so this will be A. Over here now, if we go P, Q, R, the disorder average will set P, Q, R here. This will be A and A. Over here, the fermion propagators will set this to be I, J, K, and I, J, K, and this could be whatever, B, B. Okay. They must just be set equal to each other. So A is not summed. A is the external index, but all of the other indices are summed. So let's take a look at what we would expect for this diagram. So let's call this one A. Let's call this one B. So for diagram A, how many disorder averages did we do? 2. So we expect J squared over N cubed squared. J squared over N cubed squared. Times by delta II, delta JJ, delta KK. Delta PP, delta QQ, delta RR. That is n to the 6. So this is like j to the 4. No powers of n. Now let's look at B. Again, 2 disorder averages. So j squared over n cubed squared. And now let's take a look. I is summed over, that gives us n. J is summed over, that gives us n. K is summed over, that gives us n. And B is summed over. So this is n to the 4. So this is like j to the 4 over n squared. What do you learn? At large n, you can forget that. Okay? In actual fact, the diagrams that contribute at large n always have the form that the disorder average, okay. If I ask you to look at this diagram, does that look like anything to you? Anyone know what this Feynman diagram is called? The setting sun. Kind of looks like a setting sun, right? And the point is, the disorder average must always be taken amongst vertices belonging to the same setting sun. Okay? So always between these two vertices. So the fermion average, so the fermion lines must connect the same vertices that the disorder average connects. And those are the leading diagrams at large n. So, can I clean this? Okay. So in actual fact, we've noticed a huge simplification. We don't need to bother about stuff like this. We only need to bother about stuff like this. So if we were working to second order, what would we see? We'd be able to see that plus, well, we put one of the diagrams, that. Anything else at second order? There's one more thing. You could also do this. Okay? So you can put those sunsets wherever you like, and this could be on any of the levels. Okay? But what's happening is, to get the large A limit of SYK, we need to add up all of these sunset diagrams. That's what we're summing. Now, why is this solvable? Well, it's solvable because we can actually write an equation that does the sum perfectly. So let me write the equation that does the sum, and then we'll talk about what it means. So let's define. So we were calculating this time-ordered two-point function in the full interactive theory. Let's define a function. So time-ordered correlator. This will be equal to, we've seen, we always get a delta AB coming out, and we'll call this G of T. So when I say G naught of T, I mean the fermion line without any corrections, no interactions. When I say G of T, you've summed all of the setting suns. Okay. Now, what does this g of t satisfied, you can write an equation that it obeys. And the equation that it obeys is the following. G of t1 minus t2 is equal to g naught of t1 minus t2 plus j squared integral dt integral dt prime of g naught of t1 minus t g of t minus t prime cubed times by g of t prime minus t2. This is called the Schwinger-Dyson equation. Something quite important that I didn't put in. That's this factor of j squared. That's true. So what is the meaning of this equation? How could you prove this? So we're not going to give a proof of this. It's not difficult, but it takes a little bit of time. And let's just talk about what does this mean. Okay. So what I could do is I could take this equation and I could say what this equation tells me is the g of t1 minus t2 is equal to g naught of t1 minus t2 plus order j squared. So this is correct to order j squared. Okay? Now if I've got g correct to order j squared, I can plug it in to this equation and reproduce a g which is now correct to order j to the 4. So if I take this and I plug it into this equation, what do I get? G of t1 minus t2 is equal to, so I'll get g naught of t1 minus t2 plus j squared integral dt primed. Oh, I've got the j squared. G naught of t1 minus t. And now for each of these, I'm not going to write g, I'm going to write g naught. When I write g naught, how big an error am I making? J squared. Everyone happy? But it's multiplied by j squared. So how big an error do I have in g? J to the 4. So now I'll get g naught t minus t prime cubed g naught of t prime minus t plus order j to the 4. Now what does this look like? That is just that. This second diagram is exactly what we were finding from calculating that diagram. Now that I've got this right to order j to the 4, what can I do? I can plug it in again. And if I plug it in, I'll get a g that's correct to order j to the 6. And I can see what do I get. And the terms that I get by plugging this back into that equation are precisely the Feynman diagrams that we drew at second order. Once I've got it correct to order j to the 6, I can plug it back in again and get it correct to order j to the 8. So by continually taking your solution up to some j, plugging it back into the Schwinger-Dyson equation, you can check that you're generating the complete set of Feynman diagrams in this theory. Okay? So that's one diagrammatic proof of this formula. So Kitayev, the K of SYK, he gave a diagrammatic proof just like this, that this equation is correct. Does everybody see how this equation is working and what it means? Is there anyone that would like me to say anything further? Okay, happy with that? Happy, Andrew? David?
I just want to, are the T's in the second one in the right? Are that the G0, T1 minus T2?
Oh, this should be T1 minus T. Very good. That was a little test, only David passed. Okay. Good. All right, now, this is great because this is what the function g satisfies. Can we solve this equation exactly? If you could solve this equation exactly, that would be great. Let's see if we can. And in fact, we can't. But we can solve it in the infrared. So let's see the infrared solution. So first of all, this equation is a little busy, so I'm just going to introduce a little bit more notation. I'm going to introduce sigma of t minus t prime, and this is equal to j squared times by g of t minus t prime cubed. Okay? And then what does this equation become? It says g of t1 minus t2 is equal to g naught of t1 minus t2 plus integral dt integral dt prime g naught of t1 minus t times by sigma of t minus t prime times by g of t prime minus t2. We want to solve this equation in the infrared. So in the infrared, that means low energies. At low energies, we know J, which was an inverse length, is a relevant coupling. J is going to go to infinity. So we're looking at the limit that J goes to infinity. Now if we take J to go to infinity, can you tell me what sigma is doing? Sigma getting big or small? Big. Sigma is getting huge, right? So if I look at these two terms, the only way these two terms are going to add sensibly, the only way they can be the same sort of a size, is if G itself is getting small. Because G naught is the same size as G naught, sigma is getting huge, so G had better be getting small. So in this limit, I can neglect that side of the equation. G is getting small, there's G naught, got some fixed size, plus that same size. So in the infrared limit, naught is equal to G naught of T1 minus T2 plus the integral dt G naught of T1 minus T integral dt prime sigma of T minus T prime G of T prime minus T2. That is now the equation that we want to solve. Okay, can anyone tell me how to solve this? What should this be? G naught T1 minus T2. G naught T1 minus T. We've got an integral over T. What should we set this equal to? Minus the delta function. Perfect. So if we want to solve this, this is the equation we want to solve. Integral dt prime sigma of t minus t prime g of t prime minus t2 is equal to minus delta of t1 minus of t minus t2. Great. So that's the equation that we want to solve.
Could you please repeat the argument of how you make the right-hand side 0?
Sure. Sure. So what we're saying is sigma is growing like j squared. J is going to infinity. So sigma looks like infinity squared. So we've got something, we don't know how big it is equal to something of order 1 plus something of order 1 times this infinity squared and this thing that we don't know how big it is. So one way to think about this equation is that this is getting very small, so that this times this is order 1. Then this whole term becomes order 1. That will be order 1, and this will be order 0. Will be very small. Okay? So we replace that by 0, and then we've got that equation. Happy? Okay, so huge, same size, so this must be small if those two terms are going to be the same size. If this is small, that's small, you can neglect it. Okay. Any other questions? Okay. Now, you might not see it, but that equation is remarkable. That has already got for us the second thing we wanted to see. So when we've written down this equation, we've demonstrated that this model is solvable. Because this is a closed Schwinger-Dyson equation. You could even study this numerically. What we've now shown is in the deep infrared, when j squared goes to infinity, we need to solve this equation. So we've demonstrated the model is solvable. What I want to demonstrate now is the emergent conformal symmetry. So that equation has got emergent conformal symmetry. What's the transformation? The transformation is the following. Do this. Take g of t minus t prime and replace it by the f of t dt, the f of t prime d t prime, the 1/4 times by g f of t minus f of t prime, and replace sigma of t minus t prime by, now, sigma is g cubed. So we must have the same factor that's cubed. The f of t dt, the f of t prime dt prime to the 3/4 sigma f of t minus f of t prime. Now, let's just see what will happen when we make this replacement. Okay? So when we plug this into this equation over here, you can see that what's going to happen is we have got a df of t prime, dt prime, df of t dt, because the whole thing will be raised to the power of 1. Instead of having t's, we've got f of t's. But the df dt prime will change the dt prime into a df prime. So you will end up getting a delta function on now not t1 minus t2, but f of t minus f of t2. But that will be multiplied by df dt. And you can check that that is precisely the factor that you need to convert the delta function back into a delta of t minus t2. Okay? So in this, the measure transforms non-trivially when you make the transformation from t to f, and the delta function transforms non-trivially when you make the transformation from t to f. These factors at the front here make sure that the measure in the integral integral and the delta function transform correctly. That's the last problem in the tutorial that I gave you yesterday. So try to see if you can really see that symmetry. This is the emergent conformal symmetry of the SYK model. And this is now going to help us to solve the model for the following reason. Let's choose. So the claim is that you will demonstrate that equation is invariant under this transformation, and this corresponds to changing t into f of t, and that is conformal symmetry in one dimension. Now, let's choose f of tau to be f of t to be alpha t. Okay. If we make that choice, how does G transform? Well, G of t minus t prime over into square root of alpha G of alpha t minus t prime. And if you really want this Green's function to be invariant, then it's clear what it has to do. This tells us, you would certainly guess that G of t minus t prime should be equal to some constant you have to figure out, divided by the square root of t minus t prime. So that when you scale the t minus t prime, so 1 over the square root exactly cancels with that square root. So this makes sure this is a symmetry, and we can still have our sign of t minus t prime. So that's what the Green's function would look like. So you take that for G. Once I've told you that that's for G, you know what sigma is. You can plug it into this equation and check, does this equation hold? The equation holds provided that j squared d to the 4 times pi is equal to 1/4 and pi by 4. So that's the equation you need. I guess we didn't have to write tan before. Okay. So, it's very interesting. In the UV, j squared is small. If j squared is very small, the Fermion two-point function g of t minus t prime is just like the two-point function of the free theory, so it's like the sine of t minus t prime. And if you scale your time, the Green's function doesn't transform at all. And this is consistent with the fact that we said our Fermion had a dimension 0. So in the UV, your Fermion has a dimension 0. In the infrared, j squared is huge. In this case, g of t minus t prime is like 1 over the square root of t minus t prime times by the sine of t minus t prime. Now remember, what is this Green's function? This Green's function is related to a correlator of 2 fermions. So the 2 fermions, when we scale, pick up a factor of square root alpha. So what does each fermion pick up? Alpha to the 1/4. Everyone happy? If that picks up alpha to 1/4, that picks up alpha to 1/4, that gives you a square root alpha. So actually for your fermions, in the IR, delta is equal to 1/4. So what that shows you is, in fact, this is a strongly interacting theory in the infrared. It's nothing like the free field fixed point. the dimension of your field has changed completely. In the UV, you had a dimension of 0. In the infrared, you've got a dimension of 1/4, but it's still completely solvable. You can still solve this theory exactly. Okay. So let me just say one more thing, and then you guys can take a little break before the next lecture. I just want to tell you that exactly the same thing has been done when you study the theory on a circle, meaning finite temperature. And in that case, a very similar argument leads you to g of t minus t prime is equal to b, the same e with the same value, pi over beta sine pi t minus t primed over beta to 1/2 sine of t minus t prime. So we also understand this IR fixed point at low energies. Next time we will discuss the yes law.
For the last result, does it correspond to the frame choice of f of t?
No. Okay, the last result. So what this corresponds to is this was the theory defined with time as a line. So we would integrate over time, for example, from minus infinity to plus infinity. For this theory, we're working on a circle, and we identify time with time plus beta, where this is related to your inverse temperature. Okay? So this would be for the finite temperature theory. This would be for zero temperature. Good question. Any other questions? Okay, then I think that what we will do, next time I'm going to make just 2 quick comments about the 4-point function. And the only reason why I'm still going to say something about the 4-point function is that this conformal symmetry that we found is broken for the 4-point function. So when you calculate the 4-point function, there's again a Schwinger-Dyson equation you can write down. When you try to solve that Schwinger-Dyson equation, the 4-point function in fact is divergent, it's infinite. But if you work at close to the infrared fixed point, you find out the 4-point function is then finite. The conformal symmetry is not perfect, it's slightly broken by the 4-point function. But I'm not going to say too much about that. I mean, there's lots of interesting things. This is how you would calculate, say, the spectrum of the theory. But then what I immediately want to do is talk a little bit about the quantum butterfly effect, which is maybe more interesting to see how do you see chaos in quantum field theory. So that's what we will discuss next time.